And we already did the nuclear half-life lab, so we'll see how far we get today. And then, thank you.
Welcome. It's so good to see you.
See you too.
Are you going to be around for lunch?
Oh, yeah.
You want to just stay in here or go over?
I'll go over.
Okay.
Okay. Thanks. All right, so we're going to talk about the nuclear chemistry. If she didn't go over this, were you able to finish the lab, half-life lab? Okay. All right, so we'll go through a little bit here. The first part here is just a couple videos about pros and cons, and I believe in your notes you get to write down some pros and cons for nuclear energy. A lot of people are against nuclear energy, but they don't understand all of the implications. I'm going to pause the video here because these videos don't. Who says they're for nuclear power? Raise your hand. Defend it. Okay, those against nuclear power. Those that don't know either way, because half of you didn't. Raise your hands. Okay, so those of you that are for nuclear power, tell me why. How does it save lives? Yes.
Instead of like nobody thinks of all pollution, but the other ways of you're putting out in the atmosphere, there's toxic waste in the ground, so it just toxic waste does a lot more damage. But in reality, the bad air quality gives you lung cancer and all this stuff.
Okay, so quality of life, and okay, all right. Any others? Pro. Why did you vote pro? Lasts a long time. Okay. Yes. Right, and then the waste doesn't last as long either. You notice that. A few hundred years versus a few thousand years, which is good. So if we change to the thorium reactors, we've got a lot of stuff going on. There's not been much innovation there because people are afraid of nuclear energy. Okay, if we're going to move on, we can't be afraid of it. We've got to go forward. So those of you that are undecided, what made you undecided? What things scared you about going on with nuclear energy?
Well, like I said, it's tied to nuclear weaponry, right, directly. You really can't have nuclear weapons without nuclear reactors.
Okay, so nuclear weapons get from nuclear reactants, but if we change what we're using to make the nuclear reactors, then we cut that. Okay, any others that you were sort of nervous about? Okay, I'm not here to say pro or con. There's goods and bad to everything. Okay, it just depends on what you consider the best alternative. Does that make sense? We have lots of choices that you're going to have coming up in your life. They're actually putting in a nuclear reactor in Green River. Did you know that? In Utah. Huh? Okay, I'm not sure what kind it is. So it could be nice, could be not nice. But there is a lot of uranium down in southern Utah. There's a lot of uranium mines down in southern Utah. I don't know about the thorium, but I do know there's a lot of uranium mines. And so if you happen to see a mine in southern Utah, if you go vacationing, it's probably not a good idea to go in it, because if it's a uranium mine and you're not dressed correctly, you just might be giving yourself several thousand x-rays in one excursion, which is not good. Okay, so you guys are the future. You've got to make the decision. So you need to be informed of what's going on, and that's what this was all about. So, oh my gosh, I've lost a neutron. Don't worry, you can get one free of charge. Ha 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 ha. Okay, and then when I was young, I was an atom of uranium-238. I felt so alive and dangerous that one day I accidentally ejected an alpha particle. Now look at me, I'm a spent old atom of lead-206. All my life since has been nothing but decay, decay, decay. So in our lab last time, when you were working with the M&Ms, you got to do a decay series. And what did you end up with? Lead-206. So yeah, after it lets go and lets go and lets go and lets go, we end up being a stable atom. So at one point you come to a point where you're stable. Okay, so when we have an isotope half-life, a half-life is just what it says. It's half the amount of time it takes to have half of what I started with. Okay, now if you work in a hospital, they actually do use isotopes to do different kinds of x-rays to do different tracers in your body. So when the radiologist has to order these from a supply house, he has to think, okay, it's going to take this long to get here, so I've got to include this many half-lives to get it to me. And then the patient's coming in on this day, so I need to make sure it has here so there's enough left that it will go through the body and I'll be able to see it. So they have to make sure that they get it so that when the patient comes, I have enough left to actually read it. All right? So this is what a half-life curve looks like. It's an exponential decay is what they call it. And you should have been able to do that really quickly. And your M&Ms that you used should have really mimicked that. Was that surprising to you that they both were almost the same graph? Didn't you think it would be different for each one? It was like, okay, this is really weird. This is actually strange, but it actually is a decay series. Now, here are a couple of the equations that you might need if you haven't got them down for half-life. The A is the amount that you started with. AO is the amount you start with. A is the final amount. Sometimes we put an AF. And then 1/2 to the n power. The n is how many half-lives am I going to go through. And then the second equation that we use there is T, total time. You'll want to write these down. If you haven't got these written down, you'll want to write these down because these two equations are very important to you. Okay, T is the total time it takes, and then T1/2 is how long is the half-life of whatever I'm using, and the N is how many half-lives am I going through. Now, we're not always going to end up right on a 1, 2, 3, 4. Sometimes we might end up at a 1/4 or a 1/2 or 1.3 half-lives, and so the math gets a little nasty, to put it nicely. Okay. So we have to be able to do some working with that, and we'll do some problems, and so you can see how that works. Okay, so everybody got these two equations down and what they mean? I don't want to move forward until everybody has these equations down. Emily, you got these equations down? You'll see some people writing, so we'll give you a few more seconds. Make sure you've got these down because these are what we're going to be using. As you're writing this down, you can sort of see that different isotopes, different radioactive isotopes have different half-lives. So strontium-90 has 28 years. Cesium-137 has 30 years. Plutonium has 24,000 years. Cesium has 2.3 million years, and iodine-129 has 15.7 million years. And when they're working with something in the hospital, they don't want anything that has that long of a half-life. They want something that has a half-life of 24 hours or 12 hours or 6 hours so that it can get out of the system quickly. A lot of times if you go to the hospital and you have a radioactive study, they'll say don't get around young children for 2 days or 3 days. And the reason why is because you're radioactive. Okay? All right, we okay to go forward? Anybody need me to wait? Right? So, carbon-14 is what we use a lot of times to find out how old something is. If we take something that's alive, and carbon-14 is processed through, carbon dioxide. And so as long as something's alive, it's taking in carbon-14, and it has a certain amount of carbon-14. But the minute it dies, whether it be a plant or a person, the carbon-14 goes out of it. So it decays out of it. So depending on how much something live is to next something dead, they can figure out how old that dead thing is. Okay? So let's do some of these problems. And you know me, I hate story problems, so I like to pull out what's in the story problem and then use it like a math problem. So the half-life, that's T1/2, of cesium-137 is this. So I'm going to put down here T1/2 is equal to 30.2 years. So I don't have to go back up into the problem. The initial mass of the sample is this. That's AO, 1.00 kilograms. How much will remain? So I'm looking for A after 151 years. That's T, big T, 151 years. Okay, so now look at the two equations that you had. Do I have enough for one of the equations to solve for something? Which one? You're nodding your head. But I don't have N. So I'm missing two things on that one. So what? The only other equation is what? T equals T1/2 times N, right? Well, I have T and I have T1/2, so I can solve for N, right? So I just need to divide both sides by T1/2. So N is equal to T divided by T1/2, or 151 years divided by 30.2 years. Ooh, if I don't have a calculator, I probably need one, so come grab one out of the sink if you don't have one. If you do, let's put this through and find out how many half-lives I'm going through. Is it going to be a whole number? Maybe. I hear yes, and I hear What is it? It's 5. Good. For those of you that got a calculator, it is 5. So now I've got N, I've got AO, and I can solve for A. So what was that equation? It was A is equal to AO times 1/2 to the N, right? Whoops, I put the N in already. 1/2 to the N. So now I can just plug in. AO was 1.00 kilograms times 1/2 to the 5th power. So how much am I going to have left? You think of it taking 1, dividing it by 2 5 times. If you don't have a calculator that does powers, you can do that. You can divide it by 2 5 times. Now, if that's not a whole number, you can't do that. Anybody got an answer? There were the crickets. So 0.5 to the 5th power. Well, 1 divided by 2, right? 1/2 is 0.5 to the 5th power. 0.031. Do I have a second on that one? Okay, so that's how many kilograms I have left. That's not a lot. Okay, so you just got to do it in order here. So let's go to the next one. Carbon-14 has a half-life of this many years. So T1/2 equals 5730 years. Consider a sample of fossilized wood that, when alive, would have contained 24 grams of C14. So what's that? When alive, would have contained. It has to be A or AO. Which one is it? It's AO. It's what I started with, right? When alive, it contained 24 grams of carbon-14. Now it contains, so that has to be A, right? 1.5 grams of carbon-14. Now this is where it gets a little tricky. Okay, we have to use log powers. Does anybody use that yet? In math, have you used log? Okay, so here's the equation. A equals AO 1/2 to the N power. I need to get the N down because I got to solve for it. Okay, or I can just plug in and pray that it comes out to a nice number that I can see. Either way, it's up to you. Okay, so let's put them in and let's see if we come out with a nice number. If not, we can go from there. 573, nope, that's T1/2. Try that again. A is 1.5 grams. AO is 24 grams. 1/2 to the N power. So take and divide both sides by 24. What do we get on the one side? 1.5 divided by 24 is what? Say it one more time loud. 0625 equals 1/2 to what power? Well, I can do it really quickly. 1/2 is 0.5, right? So 0.5 squared is what? That's not going to work. So 0.5 cubed, what is it? Okay, that's not it. Go 0.5 to the 4th. That's it, right? Okay, so I can solve it that way. I can get n equals 4. If I don't want to solve it that way, okay, I'm going to show you the other way real quick. I can go ahead and get to this point, and then I log both sides. So I would take log of 0.0625 is equal to, when I log something like this, the n goes in front. So then I get log, whoops, try that again. It's equal to n log of 1/2. And then I can solve for n. So that's when it's not a pretty number, when it's not just exactly a 4 or 3 or 2 or 1. I have to use that. So go ahead and let's try that. Do log of this number, what do I get? And log of 1/2, or log of 0.5, negative 0.30. So then I divide both sides by negative 0.30, and I should get 4, right? N equals 4, because the negatives would cancel, and 0.12 divided by 0.3 is 4. So either way, whatever you're more comfortable with. Now I'm probably going to not give you a 0.5 or 0.3 at this level, at general chem. But if you go on in chemistry in the colleges, they will use that. So am I done? No, what have I just found? How many half-lives? What do they want me to find? How long? So how long is a half-life? 5,730 years, right? So all I have to do is times that. So total time is just T1/2 times N. So T is equal to 5730 times 4. So T is equal to what? Say it real loud for me. I know I know that feeling. 22. It's not writing, guys. 22,920. That's what it says, whether you can read it or not, and that's years. Don't forget the unit. I don't know why there we go. Okay, so we doing okay? Feeling okay? Let's do a couple more, right? We got a couple more to do. Okay, this one I'm going to write up above because I forgot. I just centered it weird. Okay, so 64 grams of germanium-66 is left undisturbed. So what is that? 64 grams. What is the 64 grams? AO, A, T, T1/2, or N? AO. Okay, 64 grams. Is left undisturbed for 12.5 hours. What is that? Big T, good. It doesn't want to give it to me. Okay, at the end of that period, only 2 grams remains. That's the A. What is the half-life of this material? What am I looking for? T1/2. Okay, 2 ways you can do this. Since I ended up with a whole number, I probably can just take 64 and divide it by 2 and see how many times I divide it by 2 to get to 2, right? Or I can use the equations. Which do you think will be easier? either way. Okay, it just doesn't matter. So here we've got A is equal to AO times 1/2 to the N. Well, I don't have everything in that one. I don't have N. I do have A and AO. So I'm going to do the same thing I did before, which was 2 grams is equal to 64 grams times 1/2 to the N. So I'm going to divide both sides by 64. And I'm going to get a number for 2. 2 divided by 64 is what? Oh, come on, guys, you're killing me. 2 divided by 64. 2 divided by 64. You guys are giving me 32. No. Okay, what is it? 0.3125. Okay, is equal to 1/2 to the N power. Well, I don't know that one right off. I could take 0.5 and divide it by to the power of 2, 3, 4, whatever. But I'm just going to log both sides because I've got that button on my calculator. I might as well use it. Equals N log of 1/2. So what's the log of that number? Yes? Oh, is it supposed to be 0.013? Good. Catch me, guys. Okay. There's a little 0 there. Okay. And I moved my decimal, so my decimal's right there. All right. What do we get? Okay. Is equal to N. What's the log of 1/2 again? 0.5? Negative 0.3. Is that right? So I divide both sides by negative 0.30, and N equals 5. Is that right? I just did 15 divided by 3. Is that right? Okay, so then what do I need? What am I looking for again? Oh, I'm looking for the half-life. So total time was 12 hours, and I got T1/2 times N, and I'm looking for T1/2, so T1/2 is equal to total divided by N. So 12.5 divided by 5 gives me my half-life, which is 2.5 hours. So I have to sort of think it through. Okay, let's look at the next one. I'm going to do it in red just to be different. Okay, with a half-life of 28 years. So what is that? What symbol is a half-life? T1/2. 28.8 years. How long will it take for 1 gram, what's that? AO, of strontium-90 to decay to 125 milligrams. Ooh. That's A, but I want them to be in the same units. So I can say this is 1,000 milligrams, or I can change the milligrams into grams, whichever is easier for you. I'm going to do it this way. But I could have said 1 gram and 0.125 grams. Okay? Okay, so it wants how long. What are we looking for when it says how long? What are we trying to find? We're missing 2 things. We're missing N, and we're missing capital T. Which one are we trying to find? Capital T. So we're trying to find this one. All right, so I'm going to have to find N again. I'm going to have to do what I did up above. Okay, so A is 125. equals AO 1000 times 1/2 to the n. So then I take and take and divide both sides by 1,000. So I get 0.125 equals 1/2 to the n. I'm going to log both sides. Log 0.125 equals n log of 1/2. Well, I know the log of 1/2, so n is minus 0.30. And what is the log of 0.125? Hopefully it's negative, right? Negative what? Then I'm going to divide both sides by negative 0.30. And what does my n end up being this time? It's not a whole number, is it? It's a little bit off. It's what? 903. Okay, then it's going to be close to 3, right? So n will be 3. Then we just take what we did up here. Total time is equal to t1/2 times n. 28.8 years times 3 will give me how many years? How many? 86.4? Okay. You guys feeling confident how to do this now? I think there's one more. Is there one more? No. You guys have one more? Okay, go ahead and do that one more because we already did this thing last time. We bring just up a scratch piece of paper here. Take time. I want you to try and do that last one on your own, and then we'll bring it up here and see how you did. I'm just going to write up stuff first. So just as a hint, if you haven't noticed, you're going to find n first using the t and the t1/2 equation. And then you're going to find the other one. So I'll give you a few minutes to work on it. You haven't done any of it?
No, we just haven't corrected it. She couldn't find the...
So assignment number 1. Let me see if I should have it in there, but. Sorry. Okay, if you're stuck, let me know. If you know how to do this, great. Okay, just put those equations up if you happen to forget it. Yes. Mm-hmm. Mm-hmm. Now we're going to put it into this equation if you haven't already. So we've got A, but we don't have AO. So I'm going to bring this down right here. So A, oops, we've got A, 14.5 equals AO, 1/2 to the 5th power. Which is how do we end up? We do okay? Got it? Okay, so it can be given to you in several different ways, and you need to be able to solve it any way given. So if you haven't finished your lab, we're going to finish that in this time that's left. Before we do, we're going to correct assignment number 1. So if you get out assignment number 1 and pass it to a neighbor, please. We'll correct it first. I guess green is my friend today. We'll use green. Trying to give you the sharpened ones. Okay, make sure you put corrected by, pass it to a neighbor. Where's the semi-sharpened one? Okay. And then we'll have assignment 2 due next time. So I'll adjust the calendar on Canvas so that it's 1 day back from where we are. Okay? And I'm going to stop.